In this lecture, we will address a very important topic of concentration polarization, or a term which I prefer better, transport polarization. So often you would also see another term called concentration overpotential or transport overpotential. These are all equivalent terminologies. In the previous set of lectures, last 5 or so, we had looked at the various simplifications possible by considering situations wherein migration dominates or migration is completely suppressed, or how we can simplify the electrochemical transport equations via mass transfer coefficients. We will look at another topic related to transport, which is the transport polarization overpotential. Overpotential is going to be indicated by this acronym, or equivalently concentration polarization. In cases where we looked at one-dimensional analysis, the type of cell we are thinking is something like this, a trough cell. Okay, so there is a planar working electrode, and there is a planar reference electrode of equal size, same as working electrode, and there is no variation in this direction and in this direction. There is only variation along this direction. So, and one-dimensional analysis is possible. So we had looked at an one-dimensional analysis in previous lectures. So I just wanted to clarify what is the physical situation that is representative of a one-dimensional analysis. We will move on to reasons for transport polarization or transport overpotential in such a case. What we have in mind is this kind of a system, or in solution, gets transported to the electrode surface, gives off an electron to the working electrode, and generates a species O, which is the oxidized species. R indicates a reduced species. This O indicates an oxidized species. So there is an oxidized species here. And if you notice, for these kinds of transport to be possible, the concentration of R in the bulk indicated here is less than the concentration of R on the surface of the electrode. Therefore, a net transport of R from the bulk to the electrode surface is possible. Likewise, because O is generated on the electrode surface, the concentration of O on the surface, indicated by this quantity, should be greater than the concentration of O in the bulk, therefore, because of which a net transport is possible from the surface to the bulk for species O. Qualitatively, the reason why there is transport overpotential or transport polarization are these two differences. That is, the concentration of R in the bulk is more than the concentration of R on the surface, and the concentration of O on the surface is more than the concentration of bulk. Okay, this is the reason for concentration overpotential, and such a reason exists because this transport is an activated process. That is, it involves activation energy, and there is a slowness compared to other processes. There is a, let's say, time scale for electron transfer, this reaction to occur. Compared to this time scale, the time scale for this transport and for this transport is longer. Therefore, there is an inherent slowness in the supply of reactants to the electrode surface, and there is an inherent slowness in the removal of products. That is the qualitative reason. We will look at it more quantitatively in this slide. So the way to address this quantitatively is that you first consider what is the Nernst equation corresponding to the concentration of R and O on the electrode surface. So if you write out the Nernst equation, that will be this expression. Notice in these cases, we are not bothered about activation or kinetic overpotential. Okay, there might be activation barriers associated with this reaction. That is not a topic of interest now, because we are already discussed that when we looked at electrochemical kinetics, right? When we looked at Butler-Warmer equation, especially in the case of a single electron transfer, we had looked at how to address those activation over potential. That's not the topic of this lecture. We are going to assume that those are smaller compared to the activation barriers that exist for transport. So we're going to look at exclusively transport over potential or transport polarization in this lecture. So again, just to emphasize, this is the Nernst potential corresponding to the concentration of R and O at the electrode surface. In the resting state, that is, what do I mean by resting state? Okay, supposing there is no overall current flow. Okay, if there is no overall current flow, then there would be no concentration difference between R in the bulk and on the electrode surface. Again, there would be no concentration difference between O on the electrode surface and in the bulk, right? So I can write the null potential corresponding to resting state, that is where the I is equal to 0. That null potential will correspond to CO and CB corresponding to the bulk values. Okay, B indicates the bulk values. This would be the null potential in the resting state. If I take the difference, okay, why is the difference important? Let's again just go back to this expression. If I am more positive than this number or less positive than this number, I would be able to push the reaction towards the anodic region or the cathodic region. Okay, depending on where I am. Okay, with respect to E calculated using these values. If I am more positive than E, I would be generating anodic, pushing the reaction in the anodic direction. And likewise, if I'm less positive, I would be pushing the reaction in opposite direction. Okay, so these values are of significance because they are going to tell me how I will be able to generate anodic currents and cathodic currents. In principle, if this transport had been fast, the potential of relevance would be this number calculated with these values. Okay, so because of the slowness of transport, I am not able to get to this number, but I am able to get to this number, which is determined by these values. Okay, so if I subtract these two quantities, I would get the transport over potential or transport polarization, which is just obtained by subtracting these two numbers. I mean, I've retained the notations utilized in the book, but yeah, so just for continuity's sake, maybe there could have been different notations, but in any case, what we mean by transport over potential is eta transport is equal to difference between these two quantities. Okay, so these two quantities. Okay, so transport over potential is, let's now look at the value of these quantities. Because of these constraints or these facts, commonsensical facts, this is greater than 0, this is also greater than 0, right? Therefore, this overall quantity is a quantity more than 1. Sorry, this is not just more than 0, this is more than 1. Okay, again, this is more than 1 because of these constraints. Okay, so product of these two quantities is also more than 1. So this is the way we are defining transport over potential. Ideally, if there were no over potential, we would be just working with this number. Because that is not possible, we are working with this number. So the difference between these two quantities as represented here is determining the transport over potential. This is the potential that exists over and above the potential that would have existed in the resting state. Okay, this is the potential that would have existed in the null resting state, but over and above that, we have to work with potentials obtained here using these quantities. So always the Nernst potential would be greater than 0 because these two quantities are greater than 1. All right. Okay, so let's pause for a minute and then look at the network of electrochemical equations that is going to help us quantify the transport over potential or transport polarization. To begin with, we have the Faraday's law. Okay, Faraday's law helps us get to the current, and that current is, when there's finite current, that current is connected to transport equations, transport fluxes given by these two quantities, right? So that I can write in the most generalized manner as there is a mass transfer coefficient times concentration on the surface and concentration on the bulk, okay? Because this is a vectorial quantity. To get the direction right, you have to adjust this accordingly, okay? Depending upon whether it's R or O, to get the directional nature of this flux correct, okay? So I can write the transport in this equation. So T indicates transport, F indicates Faraday's law. Transport, there are certain transport laws which are going to give me these two fluxes. And then there is a Nernst equation or a null Nernst equation that I can write based on the bulk values or based on, which would be, if I write the Nernst equation based on the bulk concentration, this and this, that would be only of relevance in the resting state. Okay, that is the null potential at the resting state. In other cases, when the activation over potential is much smaller, or if we neglect that, I can write a Nernst equation based on these two quantities as I indicated in the previous slide. Okay. So difference between those two quantities, the Nernst potential written with these two quantities and the null potential in the resting state, would give me the eta transport, which is the transport over potential or transport polarization. All right. So typically, this quantity is hard to measure because I really do not know what is the concentration at the surface, okay? Because I don't know that quantity, I can use these, there are two equations here, right? One corresponding to R and another corresponding to O. I can use these two quantities to eliminate COS and CRS, okay? I can substitute those two equations into this equation and then write this equation, right? This is simple substitution. When I write this equation, what do I get? This expression, we can also impose a mathematical constraint because what is inside the lawn has to always be greater than 0, right? This can never be negative, it's ill-defined. Therefore, I can impose certain mathematical constraint on these two quantities because these two quantities have to be greater than 0. So the mathematical constraints are the following, okay? If you notice these two mathematical constraints, that is, we are providing a bound for I has to be within these two values so that these quantities are well defined. These have a physical interpretation also. What is the physical interpretation? We've already looked at these two quantities. These are the anodic current density and the cathodic limiting current density. This is the anodic limiting current density. This is the cathodic limiting current density. If you look at these two expressions, that's what they mean. This is the maximum current that can be obtained, anodic current that can be obtained. This is the maximum cathodic current that can be obtained. All right. So, and that exists, that is, these two limits of limiting current density exists because of mass transfer limitation, because there are inherent activation barriers associated with transport, inherent slowness associated with transport of the reactants, and evacuation of the products from the electrode surface, and because of which we can define a overpotential and a limiting currents corresponding to anodic and cathodic currents. All right. That's why the current tends to plateau off. Okay, even though the potential increases, there is a limit to which I can transport the reactants to the surface and I can evacuate the products from the electrode surface. Okay. So mathematically, all this information is in this equation, and we can rewrite this in a conventional form based on E half. Okay. E half is defined as this quantity. Okay, current corresponding to this quantity is called E half or halfway potential. Okay, halfway potential is in between the current corresponding to average current between these two values, these two bounds. These are the two maximum values I can get in the anodic and cathodic regions, and this is half that current. Okay, and the potential corresponding to that value. Okay, I can rewrite this where E half is given by this quantity. These are all very trivial mathematical rewriting. There's nothing, no more conceptual content to these equations. There's all various forms of the same equation. Okay, so with this we have completed the presentation of transport overpotential or transport polarization. We started this journey of polarization overpotential, if you remember, with this slide. Okay, so that is, we presented this figure many lectures ago, and we said in electrochemical systems there are three kinds of overpotential. This is the simplest. We presented this first, There is the ohmic overpotential. There is the IR drop that exists in the bulk of the electrolyte. Then, over a few lectures, we presented the reasons behind kinetic. This refers to kinetic or activation overpotential or activation polarization. That would have this form, okay? And then there is this eta transport, which we presented in this lecture, okay? So every curve, if you notice, there is a linear part, there is an exponentially raising part, and there is a part of the current where it plateaus off, okay? So all parts of the response of the current to variation potential can be understood by these three polarization mechanisms or overpotentials. Okay, so you can all parts of I versus E, which is in effect, that's what you tend to measure, right? If phenomenologically, what is measured in an electrochemical experiment is I in response to variation of potential. Okay, to understand I versus V behavior, we have elaborated three polarization mechanisms and when all these three are put together, all aspects of I versus V behavior can be understood. With this, we will wrap up this lecture and just think through this. Okay, this is an important juncture of the material that is presented because all three aspects of polarization have been presented. Okay, these are the three main polarization. Okay, supposing we can have additional polarization mechanism, additional overpotential. For example, when you're thinking about, let's say, electrodeposition, okay, there can be activation energies corresponding to crystal formation, okay, electrocrystallization. Those may have additional overpotential. These are more specialized cases, okay? But what is common, okay, what are the three fundamental overpotentials common to electrochemical systems are these three overpotentials. So as we have completed the discussion of all the three overpotential polarization mechanisms, you should pause and make sure you understand all three polarization mechanisms and how do we quantitatively discuss these three mechanisms. With that, I will stop here. Thank you.